So, first of all, good morning, everyone. A very warm welcome to all the participants joining us today. On behalf of MIT College of Railway Engineering and Research Barshi, I'm delighted to welcome you for today's insightful webinar on computational fluid dynamics, introduction and case studies for the engineering. We are glad to see such an enthusiastic participation from students, academicians, and professionals. Before we begin today's session, let's take a moment to the positivity with a world peace prayer. I now invite our technical team to please play the world peace prayer.
नमो जीयाद्या वेद प्रतिपाद्या जय जय स्वसंवेद्या आत्मरूपा देवा तूची गणेशु सकलार्थ मति प्रकाशु म्हणे निवृत्तिदासु अवधारी गोदी गुरुर्ब्रह्मा गुरुर्विष्णु गुरुर्देवो महेश्वरः गुरुः साक्षात् परब्रह्मा तस्मै श्री गुरवे नमः। पूर्णमदः पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते। ॐ शान्ति शान्ति शान्तिः।
Thank you all for joining us for this. Now, I'm now honored to invite our Honorable Principal Sir Dr. Madhukar Lengre to address the gathering. Please, sir.
Good morning, all. Our esteemed speaker, faculty members, students, and all participants. It gives me immense pleasure to welcome you all in insightful webinar on computational fluid dynamics, introduction and case studies for engineering. On behalf of MIT College of Railway Engineering and Research, Barshi, I extend my warm regards to everyone present here today. Our institution is committed to providing quality technical education and nurturing innovation, research, and practical knowledge among the students. At MIT College of Railway Engineering and Research, we continuously strive to create opportunities where students can go beyond textbooks and connect with real world engineering challenges. Webinars like this play a vital role in bridging the gap between academicians and industry applications. The topic of today's webinar, computational fluid dynamics, is highly relevant in modern engineering. It helps us understand and simulate complex fluid flow and heat transfer phenomena, which are essential in industries such as transportation, energy, and manufacturing. I am confident that today's session will provide valuable insights and inspire you to explore advanced concepts of in this field. We are honored to have with us Dr. Sanjay Gaikwad sir, an experienced academician and researcher within more than 15 years experience in CFD and heat transfer. So we sincerely thank you, sir, for your sharing your knowledge. Once again, I welcome you all and wish you very productive and enriching session. Thank you. Best wishes everyone for today's webinar.
Thank you so much, sir, for your encouraging words. So moving forward, it's now my privilege to invite Dr. Sanjay Mane sir to introduce our esteemed speaker for the day, Dr. Sanjay Mahadev Gaikwad sir.
First of all, thank you, ma'am. First of all, I would like to welcome Dr. Gaikwad for this wonderful webinar series, which is organized by MIT College of Railway Engineering and Research, Barshi. So I would like to talk about few things related to the speaker, Dr. Gaikwad. So Dr. Gaikwad is currently associated with Army Institute of Technology, Pune. So he has 15 years of teaching experience and 1 years of industrial experience. He has research exposure also. He has published more than 30 international national journals, also more than 15 international national conferences. He has also received 5 patents, and also he has served as consultant trainer for CFD. So with this lot of experience in the CFD domain, particularly in the microchannel, so with us we have the expert Dr. Gaikwad. Now I would like to invite him to have a words to have guide our participants. So those who are new in the CFD domain, they will get in-depth knowledge about how to simulate it and how to get the practical case in studies. With this, I would like to thank you for the sessions that the Dr. Gaikwad has accepted and are available for this webinar. Thank you so much, ma'am.
Thank
Sir,
you
I
so
am.
much, sir.
Yeah.
Now, without further delay, I request Dr. Sanjay Gaikwad sir to kindly take over the session. Small note for the participant. If you have any questions, please feel free to post them in a chat box or we will address them during the Q&A session. Sir, the platform is yours.
Thank you, ma'am. Thank you, sir. I'm sharing my screen. Just wait a minute. Yes. Is it visible to everyone?
Yes, sir, it's visible.
Okay. So, welcome to everyone. Today's session is related to computational fluid dynamics, introduction and case studies in engineering applications. So, myself, Dr. Sanjay Mahadev Gaikwad, and Associate Professor in Army Institute of Technology. Already, sir has given introduction about me. The PPT is related to uh, the software which is concerned from ANSYS. So I have mentioned the resources that is from ANSYS Fluent. I am referring. Okay. So the first uh, thing is that what is mean by CFD, computational fluid dynamics? What is mean by it? It is a science of predicting fluid flow, heat transfer, mass transfer, chemical reactions, and related phenomena by solving mathematical equation that represent physical law using numerical process. When we talk about the physical law, what is mean by physical law? So there are a few laws, just like a Newton, uh, just like a conservation of mass, momentum, energy. In few cases, spaces transfer and other part. Before that, why it is required in a engineering point of view? Why CFD is relevant? Because here conceptual study of new design we can do, detailed production development, and where we required some sort of troubleshooting, and if required we can redesign the things. So CFD simulation play a vital role in product development, process industry, where we can save the time for more experimentation or testing purpose. So It reduces the total effort required in laboratory. That is the best concern in a CFD. So I will just go through the different applications because there are many students in this webinar who may think that where CFD may use, what are the application. So first we can see the application. The first application, that is aerospace, from where this computational fluid dynamics branch innovate or start. In aerospace, you can use it for separation of boundary layer, hypersonic launch vehicle, then wind body interaction. Wind body interaction means solid and fluid when they interact with each other. What kind of flow physics will be there that you can observe through this image also. So the first application always it comes in everybody's mind, that is aerospace. Second application, appliances. As we have seen, you may observe that everybody is having a refrigerator at their home. So in that refrigerator, the cooling phenomena happens, and somewhere at the top you can see freezer zone. You may find that there are some ice formation is there because of some problem. Then how we can fight with that ice problem? So no frost refrigerator one can design by CFD simulation. We can predict at what time the freezing happens. So this is the application related to appliances, refrigerator. The next application is automotive. As we know, the automotive sector is widely spread in and around the India. And when, as a mechanical engineer, we always think that how I can how I can contribute in the field of automotive sector. Then one may think that he may become a design engineer where he will design the n number of parts which are used in automotive sector. Then there is another domain called as CAE domain where structural analysis is used. How much load will be there and how much bending moment will happen. That comes in structural design, structural analysis. But the things comes when we are looking at the comforts of the passenger. Then here you can see the interior ventilation. When you switch on the air conditioner from the car or vehicle, whether that air conditioner can blow air so that each and every corner of your car or vehicle give the comfort condition. That kind of simulation you can do. External aerodynamics play important role when we are trying to design the car from the exterior point of view, because unnecessary you are designing something, you may think that it is a looking goods, but it may create drag and lift phenomena which may cause the excessive fuel consumption for your vehicle. So for that purpose, external aerodynamics play important role. Then there is another phenomena called as undercarriage aerodynamics. As we know that engine is the hottest part in the vehicle. Even though inside the cabinet you may feel very condition because of the air conditioning phenomena, but the hottest part is engine. Through engine, the exhaust is going to atmosphere through silencer. So that passage, it means undercarriage aerodynamics. If you are willing to simulate, that also you can do in CFD simulation of aerodynamics. Then we come for the engine cooling. Why engine cooling is required? Where is the maximum temperature of engine? Obviously, where the combustion happens. That is cylinder head. And that's why we are aware that that cylinder head is cooled with liquid cooling. And if you are willing to go for such kind of simulation, whether that liquid cooling is sufficient or not, that kind of simulation one can do in a CFD simulation of automotive sector. Biomedical, where I can say biomedical, you may surprise that how a CFD engineer can work in a biomedical. Definitely. But CFD engineer is used anywhere where there is a fluid and heat interaction is there. You can simulate blood pump. You can see this is blood pump simulation. Then temperature and natural convection current in eyes flowing the laser heating and spinal cathode. This such kind of simulation one can do in a biomedical field also. Chemical processing. This chemical processing is not something different than mechanical engineering. Heat exchangers, shell and tube heat exchanger you can predict. So this is flow separation. Then twin screw extrusion modeling. Then shear rate distribution in twin screw structure simulation. It means anywhere where interaction of fluid to fluid or fluid to solid, there we can use this CFD in a chemical processing also. HVAC, heating, ventilation, and air conditioning, and refrigeration. Nowadays, we can see that air conditioning is widely used anywhere where comfort is essential part. The first example, workstation ventilation. Second example, that is contours inside the location of fresh air supply and flow path line colored by pressure quantity head loss in a duct. So all these applications are related to air conditioning part. That air conditioning may be a central air conditioning. That air conditioning may be a window air conditioning. So it means this ventilation, heating, ventilation, and air conditioning is very much important in CFD field. Next, hydraulics. This is example related to civil engineering also. When flood happens, if this dam breakdown or leakage breakdown, then what will happen? What kind of pressure will exert on the wall and how the breakage will be there and what will be the after phenomena that one can predict in hydraulics. In hydraulics, there are turbines, pumps that you can also simulate. It is not restricted to this dam. So you can take any example in hydraulics that can be simulated in the CFD, computational fluid dynamics. Marine engineering, ship. While designing the ship, you can optimize the shape of front space of the ship through CFD simulation. Then oil and gas. This oil and gas here, separation of two fluids. When we are trying to separate multi-physics problem, then one can use, so this example, flow vectors and pressure distribution, offshore oil rings, then flow distribution, flow of lubricating merge or a drill bit, and here volume fraction of multi-phase separator. So such kind of simulation one can do in where oil and gas application. Power generation, flow in a burner, flow pattern through water turbine as I mentioned. It is also comes in hydraulics. Then flow around the cooling towers and path line from the inlet colored by temperature during the standard operating condition. How the flue gases will pass through the chimney, that one can simulate. And in sports also, when any swimmer swim inside the water, what kind of forces exerted on the palm of the hand or whole the body, that one can simulate. So these are the few applications where one can say that CFD is used. Then what is how it work? That is also important. And before that, I would like to show you why we should go for a CFD. So simple, I will draw one example. So this is a flow through pipe, flow in and flow out. This is experimentation part. In experimentation, where you measure the property at inlet and outlet. So I can measure the property just like P1, pressure, temperature, velocity. Same way at outlet, pressure, temperature, velocity. And somebody want any property he can measure. So this is the way how we do the experimentation. Then suppose anybody want, no sir, as this length is 1 meter, I want more sensor to place at a different spacing. So I want more sensor. So I'm adding more sensors, and suppose inside this tube there is a one obstacle. So now what we have to do, as we required more sensor means the economics will hamper. It means I required more cost, more budget. If anybody say, no, I want more sensor, one few more sensors, then it will increase the complexity in a manufacturing also. To avoid this, to avoid this, one can go for CFD simulation. In CFD simulation, what we used to do, we divide this domain in small parts. That part is nothing but the mesh. So I can divide this total domain in small parts. So likewise, I am dividing. So try to understand why we are going for CFD. That is most important. So likewise, I am dividing this domain in 1, 2, 3, 4, 5, 6, 7, 8. How many parts? 8 multiplied by 3. Near about 27 parts. I have divided this domain in 27 parts. Then I can get the information of each from the center of this mesh. Then I can say that I can have 27 sensors inside the whole domain. But if experimentally we want to add the 27 sensors, then it will be very difficult. If you want to observe what is happening behind the obstacle, suppose I will fill this with color, then definitely you should have more mesh near to the obstacle so that you can capture more flow physics, and I can increase the mesh count. Likewise, I can increase the mesh count. So as I increase the mesh count means I can increase the computational time for my computer also, so that I can increase the accuracy. So whatever the grid I form, that is nothing but the mesh. So what is mean by mesh? Mesh is nothing but the discretization of total domain in small part. And for each part, I can solve whatever the equation we are talking about. For each mesh, we are solving the equation for conservation of mass, momentum, and energy. And likewise, we solve the total domain and we will get the solution. So that's why to get the smallest change happens inside the domain, and if we are willing to observe that flow physics, then one should go for CFD simulation. So we will. I think this part is clear. Why is more important? As somebody is showing that tool, that is not required. Whether you are willing to use that tool to solve your problem, then and then you can use. So that's why to avoid excessive experimentation, which may increase the budget, economics, and time also. To avoid that, we will work on a CFD. How it work? So it will work on a finite volume method. When I can say volume means, here you can see the control volume, 1 cube. So likewise, this total domain is divided by small cubes connected with each other. So this is called as mesh, and mesh is nothing but the discretization of entire domain in small cube. And we will use this equation where unsteady term is there, convection term is there, diffusion term is there, and generation term is also there. But all these equations are used in one problem? Not necessary. Suppose I am using only flow physics, flow through pipe, flow through channel, there is no contribution of heat, then only energy equation will be used. Sorry, only continuity and momentum equation will be used. Energy equation is not required when there is a no heat transfer phenomena. So this this equation, this number of equations are used to solve the entire domain of our simulation. Okay. Now this is the architecture of CFD simulation. What is mean by architecture? Architecture means how this CFD modeling is divided. So CFD modeling is divided in a three component. One is pre-processing, where geometry creation, solid modelers means you need to draw the geometry. Then after geometry, you go for a mesh. That is means discretize the total domain in small part. That is nothing but the meshing. So this is the first part, pre-processing. Second, solver. And these three processes are same in any analysis tool. Either it is CFD or CAE. So first is pre-processing. Second one is a solver. Solver means whatever the geometry you are using for that geometry, what type of equation you will going to use depending on rightly as per your application, whether you are solving for energy, mass, momentum, or steady state or unsteady state, whatever. So that comes in equation, which type of equation you are solving. Then the another input for this, physical models. What is mean by physical model? You may aware that in fluid mechanics, there is a Reynolds number, and that Reynolds number decide whether flow is laminar or turbulent. When flow is laminar, at that time Reynolds number value will be less than 2000, and when flow is will be the turbulent, at that time Reynolds number higher than the 4000. So that is nothing but the turbulent model. Whether you are doing combustion phenomena, radiation, if you are taking the example of solar panel, heat transfer with a solar panel. On solar panel, we are aware that the whatever the heat coming on the solar panel is because of the radiation from the sun. That phenomena you can solve with a radiation model. Multi-phase means water plus vapors. If you are willing to simulate the refrigerant which is passing through the evaporator coil or condenser coil, then you can use this multi-phase phenomena, or phase change phenomena is also you can use. Moving zone or moving mesh, when there are simulation of blade of fan will going to move at that time, moving zone or moving mesh phenomena will use. It means one person cannot work on each and every physical model. That is a constraint. You may ask me that, sir, have you used all model? No, not required. Because I am not going to solve a simple tutorial. I want to solve the problem which required to resolve, or I want a solution. Then whatever the problem coming to me, I need to categorize that problem comes with which physical model, just like a combustion. Suppose anybody willing to go for combustion phenomena inside the cylinder head, piston and cylinder head, then obviously there will be turbulence with combustion, and there will be a phase change phenomena will be also there, because if some phase liquid to vapor, vapor to liquid happens, at that time phase change phenomena will also there. And as piston will move from top to bottom, top dead center to bottom dead center, at that time that moment one should capture, that moving zone or moving mesh will also use. It means problem will decide which kind of physical model one can use in solver part. And again, what it required? material property, whether that material property may be solid, fluid. Suppose anybody uh, will going to use the derived material. It means nanofluids. Nanofluid is a combination of nanoparticles, solid nanoparticles plus water. And if anybody willing to use such nanofluids, then inside the solver there is a no as such nanofluid is defined. At that time, you need to calculate the property of nanofluid by using correlation available in open literature and use that property as the input for your solver. Then boundary condition, definitely as we are solving the continuity equation means something is coming and something is going out. It means what is mean by something? It means that may be a velocity input, that may be a mass flow rate input, that may be anything, that anything we should know. Because if we will not give any kind of boundary condition, then how that whatever the equation we are taking into the consideration, how that equation going to solve? So for that purpose, boundary condition is most important. Next one is that is the initial condition. Before starting the simulation, what should be the initial condition of your domain that you need to define, that is called as initial condition. So this way, what are the different inputs? Input are inputs are physical model, inputs are material property. When we give such kind of inputs, then and then our equation will going to solve. Yes. So one of the participant share the error, typo error. 8 into 3, 27. I have written 24. Sorry. So it is mistake from my side. There is no problem. Okay. So once we give such kind of input, then it will solve the equation. Once we get the complete the solution, then post processing is the important part. As we are aware, we do excellent work, but unless and until we will not going to present in a proper manner to somebody else, maybe our higher authority or maybe the person who will going to evaluate us, then when CFD is a concern, when we get the solution, then post processing, it means how we can represent the results, that is also important. For that representing the results, post processing, in which we can take plots of vectors, contours, and animation, that we will see in a next slides also. Then the basic steps. When we are going for any kind of simulation, CFD analysis, one should think on these 7 steps. Three steps in pre-processing and 2 steps in solver and another 2 steps in post-processing. We will see one by one. When I can say define your model or goal, why we will going to use CFD, then we should ask few questions to us, to yourself. What physical model will need to include in your analysis? Physical model means turbulent chahiye, turbulent, then radiation model or any model. What kind of model you require? What simplified assumption do you have to make? As most of the cases, what happens? The flow physics will be more complicated at that time. And as a beginner, if you are willing to solve that problem, then definitely you can try to simplify the problem initially. One simple problem will solve, then you can add the degree of difficulty inside the domain. So that simplification is required. Do you require unique modeling capability? What kind of things is required? Whether you are willing to use commercial software or something like a coding you want to do. What kind of degree of accuracy is required, and what is your time domain or time span? How much fast you require? That is also important. Being a researcher, we know that we are having lot of time. It means for undergraduate project, we are having 1 year. For MTech, again 1 year. And for PhD, there is no limit. But it is not the same case with the industry. In industry, they specify the time domain. Yes, within a 3 month, within a 2 month, you need to complete this project. And depending on that, they mention the accuracy level also. And this is a very much important. When anybody asks, I'm sharing the figure geometry to you, and could you help me to solve this problem? Then I need to ask this much question to my client who share the problem. So that is the first step. That is a define your modeling goal. What exactly you want to do in a CFD simulation. Next is identify the domain you will going to model. This example is cyclone separator. In a cyclone separator, gas is coming from the bottom side. This is a riser. Then it goes to cyclone separator. And in cyclone separator, what happens? The dust particle comes down and only gas will move up. So this is the practical, you can say, flow physics behind it. Then somebody says that this is the geometry and you want to simulate it. As a CFD engineer, what is your duty? So you need to ask the client that what kind of information at the boundary you are having. It means I should know what is the gas temperature, velocity, or mass flow rate which is coming inside. That I should know. Then can you extend the domain to point where reasonable data exists? It means whether you required all this simulation or can I model only cyclone separator? So this is the modeling of cyclone separator, not another extended part. Because we know the dust particle will going to move down, and with the riser, no need to draw the geometry up to this riser. You can cut that riser up to this end and give the input condition. What is the velocity or mass flow rate coming inside the cyclone separator? And it is moving outside the atmosphere, then pressure outlet will be there, and the remaining dust particle by gravity it will come down. So this is an inlet, one outlet and another outlet. There are two outlet and one inlet that one can model. Again, simplify domain. Whether you require 2D or 3D, that is also a concern. Because when we move 2D to 3D, third dimension play an important role. It means all geometry will change, and same time the computational grid mesh will be increased and the computational time will increase. So that one need to take care of. That is identify the domain you will model. How much I require? that I need to decide as a CFD engineer. I will give one example. One engineer came to me and asked me, sir, I want to simulate the burner. I can say, okay, no problem. Then he came with me the assembly of total burner. In that assembly of total burner, there are 1,000 parts, starting from foundation, nut and bolts, everything. Then I asked him whether you know the name of the part of this burner. He said no. Then I can request, no, it will not work. You should know the each and every component from the domain, whether it will take part of your flow physics, that you should know. And we required near about 1.5 months to clear that geometry. Whatever not required parts, I need to remove from that geometry. And literally, we required 1.5 months for meshing process only to decide what is my exactly flow domain inside the total assembly. So that is the difference between the design engineer or CAD engineer and CFD engineer. CAD engineer give you total supply, total geometry, including nut, bolt, whatever you require, whatever the things is there in the assembly drawing. But being a CAD engineer and CFD engineer, you should differentiate. Being a CFD engineer, you should think that I required only the component which take part in a flow physics. So that is nothing but the identify the domain you will going to model. Then obviously grid. Grid is nothing but the discretization. So there are different types of grid or mesh, triangle mesh. Then it is a quadrilateral mesh. When this 2D mesh become a 3D mesh, then triangle mesh become a tetrahedral, quadrilateral mesh become a hexahedral mesh. Then pyramid and prism mesh or wedge mesh are the different types. So your flow physics domain will decide what kind of mesh is required. As there are n number of mesh, just like tetra and hexahedral mesh in a 3D. Here, there are different questions. How complex is geometry and flow? If geometry is simple, then I can use hexahedral mesh. If geometry is something curvature or something else, then I can use tetra mesh. Then, as I mentioned that if you add a number of mesh, it will require more computer memory. And that computer memory will consume your time also. That's why the selection of grid is also important parameter in your problem solving. So here you can see simple mesh, and here you can see the complex mesh. It means hybrid mesh. Tetra mesh and hexahedral mesh are also used. So whatever the message in a chat box, we can take that message at the end of the session, no problem. You can see here again complex tetra mesh near where flow physics phenomena is important, and hexa mesh are used where only a simple geometry like a circle is there. So it is a hybrid mesh combination of hexa and tetra mesh. Okay. Now setup for numerical. Setup for numerical means model means we need to select which kind of flow physics we require. turbulence model, combustion model, multi-phase model. Which type of material you required, solid, fluid, or mixture. Then different operating conditions and boundary condition. What kind of boundary condition are there? So that is nothing but the setup of numerical model. And after that, after setup of numerical model, then computer will do its own part and it will solve the equation and it will give the converged solution. What is mean by converged solution? When each and every mesh will going to solve, when P1 V1 equal to P2 V2, that is nothing but the continuity equation. Continuity equation. When that continuity equation, momentum equation, energy equation solve totally, then the message will come that so your solution is converged. That is nothing but the end of your solvent part. Once the end of the solver part, then next is post processing, where you need to examine the results. Whatever the pressures, momentum, or surface, surface temperature, whether that surface temperatures are accurate or not, that you can do with the visualization tool which are there. That is, and with the visualization tool, you can predict whether that temperature is accurate or not. And if it is not accurate, then again you need to revise the model. Where is something is lagging? Either it is lagging in a geometry itself or in a mesh or something called as something change in a flow physics. Whether it is a turbulent flow, unsteady flow. If you are taking only 2D, then it may be an effect of 3D also. It may be a problem in whatever the boundary condition you are selecting. And it may be a problem in whether the grid, number of grid is accurate or not. So to check the grid adequate or accuracy, one can go for a grid independent study or grid sensitive analysis. Then and then you can come to know that whether my grid optimization is accurate or not. It means my solution is not depending on number of grid, number of mesh. So that is nothing but the grid independent study that you can do in a revision of the model. So this is the total cycle of any product development, any process development. That is from 1 to 7. Now we will see one case study. This case study is from my PhD work, that is a parallel microchannel heat sink. That parallel microchannel heat sink, this is the parallel microchannel heat sink, you can see in a figure. And the outer domain is called as a manifold. And that manifold, this microchannel is fixed. This manifold contained the water is coming from this end. It will collect in this head, water inlet part. Then it will pass through the channel and again it will go to the outer domain of the manifold. It means total geometry is like this, and I want to go for a heat transfer problem in a parallel channel. Then again, as a CFD engineer, whether I required this outer box to simulate the microchannel, not required. Because my aim is to find out the heat transfer from the microchannel itself. Then I need to select only this part, this channel. This channel is here. Again, there are some extra parts because for the sensor. So you can see the holes are there. That holes are required to insert the sensor for the temperature so that I can get to know that how much temperature of the base. And you can see in the manifold, there are again few sensors are there to measure the temperature of water when water come inside the domain, when water coming to the channel and when water passing through the channel, I need to measure the temperature. So there are inlet temperature and outlet temperature also there. And there are few sensors which measure the temperature of heat sink. So what is my data with me? There are 5 channels, channel width 1.2 mm, height 5 mm, spacing between two channel is 1.2 mm, and that heat sink is 15 mm by 15 mm. It is a very small, and I would like to show you that heat sink which is with me, because people may observe, people when anybody think about the problem, people want big problem to simulate. Now you can see the heat sink inside the camera. You can see this is a small 15 mm by 15 mm. So this much small channel is there. So this is one channel and this is the another channel. So such kind of channel is made by or manufactured by electric discharge machining. Whatever the copper you can see, that is electrodes, and workpiece will be this aluminum, and you can see there are 3 holes to measure the temperature of that heat sink. Now problem is like this, then how we can do the CFD simulation, that we will see. What is known to me? Known is that is velocity inlet, that is 0.1 meter per second, and heater input, that is 20 watt, and total dimension 15 mm by 15 mm, and height is 11 mm of that total aluminum heat sink. Then for that purpose, I need to do everything, that is a pre-processing. What I need to do? Geometry creation and meshing, solver, fluent. I need to take here laminar flow because Reynolds number less than 2000, and in post processing I can see vectors and contours. So let's see what one can do in a pre-processing. Pre-processing, one need to draw the geometry like this. Then after that, one should go for a meshing. Tetrahedral mesh are used. So this is pre-processing part. Then solver part, we need to import mesh energy equation. One need to on, that is the model we are talking about. Laminar viscous model is there. Then about material, liquid will be there, water liquid. I can select from the Fluent database. Then fluid will be the water and solid will be the aluminum. Then inlet boundary condition, I should mention how much velocity and the temperature. So velocity 0.1 meter per second. Then most important part is at the base of the channel, I have put heater, 20 watt heater. So 20 watt heater and the base dimension is 15 mm by 15 mm. It means heat flux, how I can find out? Watt per meter square. Watt is a 20, and you can convert that 15 mm by 15 mm, so mm square into meter square, and find out the heat flux. That will be 5 times 444.44. So that much heat flux I need to use at the source. Then reference value, it means initial boundary condition. If I mention, and if I go for a solution, when I will get the solution complete like this message, then I can say my problem is solved. And I can go for the results, that is a CFD post. I can take the snapshot, or you can say cut section, by creating the plane, and along that plane I can check the pressure contours, how much pressure is there. Obviously at the outlet, atmospheric pressure outlet is atmospheric pressure, so at inlet is here, and remaining solid part you can see there is no pressure. But you can see temperature distribution in a solid part, inlet at 299, and outlet you can see this range near about 303, and maximum temperature is 305 Kelvin. So such kind of vectors, such kind of contours one can get when one can do a CFD simulation like this. Temperature contours and animation, one can you can plot the temperature from inlet to outlet, how much it will be there. Then what we will do, we will do a CFD simulation of microchannel. So I will go to ICM CFD. So this is ICM CFD. It start with the points. My screen is visible to everyone. Anybody can?
Yes, yes, sir.
Yes,
It's
yes.
visible.
Thank you, sir. Thank you. So again, I can minimize this screen because I need to show the major screen. So my problem, I need to draw the geometry. So it start from points, line, surface, and volume. It is very simple tools, more simple than AutoCAD, 3D and 3D, just like a CATIA Pro E. That is very good software. But this is a tool we required for drawing simple geometry. You can create the geometry anywhere and import. You can go file, import model, or import geometry in the form of strip and IGS. So you can import in that way also. But a simple geometry you can draw here. So 0, 0. This is the 0, 0 point. What is the height of my channel? My channel height is 11 mm. So in the Z direction is 11 mm. Y direction 11. Fit to screen here. Then X direction again 15 mm. And if I can Y0, then I will get. So this is the total size. Height 11 mm and length is 15 mm. Okay. Now I can extrude this for 15 mm again. So what I will do, I will copy this point. I will copy, just a minute. I want to copy this point only. Yes. At how much distance? 15 mm, because in Z direction, there is a 15 by 15. So now I can use extrude command, just like a CATIA and Pro E, point 1 to point 2, and I will select this domain. So likewise, and I will close the remaining part. With a simple surface, now you can see this is a total duct is there. So what I will do, I will join, what I will do, I will off the surface and I will join the surfaces. If you go to wireframe, you can see surface is there, another surface. So likewise, I can create the box. Now I want to draw the channels. So I can take the length in the z direction, x direction. Now, how much spacing is there? 1.2 mm spacing is there. So what I will do, I will copy this point, 0.6 mm in z direction, 0, 0.6 mm, sorry, in a z direction. Yes, it is here. Now, channel width, channel width is how much? 1.2. Just a minute. Channel width is 1.2. So 1.2 in a z direction, that is the width of channel. And how much it is having height? 5 mm. So again, I am selecting these 2 points and transfer this point in y direction. How much? 5 mm minus 5 mm negative. So this is the way how I can create one channel. Join it. Okay. Now I need to transfer the channel to the other end. For that purpose, I can copy this point to 15 mm in x direction, because I need to do extrude operation. 15 mm in x direction. Now you can see, and I need to extrude operation. Again extrude this point to this point. One, just a minute. This point to this point. One, two, three. So likewise, I can create the channel. So how many channels? There are 5 channels like this. So what I can do, I can copy and translate these channels. So here I can do copy. Just a minute. I can dismiss. I can place this geometry in a such a way that it will be easy to copy me. Yes, yes, right. Yes, copy. How many units I required? Only here it is 1. Again, I required 4 units because total channels are 5. And how much distance I need to take in the z direction? It is 1.2. Offset 1.2. Let me check. Undo. It should be 2.4. Continue. Let me check how many number of copies there I have become it. Just a minute. Okay. I will copy one by one. 2.4 plus again what I will do, it should be copy, but right now this function is not working. No problem. So again I will copy. Yes. 4.8. Yes. Now there is a excessive copy, so I will delete that excessive part. So delete this surface, which is not required. Okay. Few things excessively copy, no problem. One can delete. Only this much part is required. So I will delete. So delete surface, delete line. You can do like this. Okay. So this is the channel which required. So delete this point which are not required. I can save this image, file save as a project. I will save at the desktop. I can say hit sync, save. So once I do like this, then I need to define which are the inlet and which are the outlet. So inlet should be at this end. Inlet should be this end and outlet will be the opposite. And again, I need to define the fluid, which is solid and which is fluid. So for that purpose, extra line it is there. So I need to delete it. Okay, let it be. So where is below the channel, there is a solid. So I need to define solid first. Solid. Where is solid? Just below the channel. And when you are giving such domain name, then it should be always inside the volume, not on the surface. Okay. So that care you need to take. Then I need to define the fluid. So what we will do, we can go for a build topology so that I can separate the overlapping surface. Just a minute. I think it get out. So just I can open again. ICM. Already we have saved the geometry, so there is no problem. Open geometry. Desktop. Hit sync. So this is the purpose to save. Otherwise, what happens? We need to draw again and again. So to avoid that, we used to, so we need to go in the build topology. Here the first option, say apply. This build topology create, just a minute. Again, I will open. Just a minute. File, geometry, open geometry. Again, we'll go to that. Okay. So we'll not do a build topology part. So we are at this point where we need to define the domain. So solid is the bottom part of the channel. Save. Desktop. Hit sync. Yes, overwrite. Okay. Then where is the fluid? Fluid is inside the channel. So that also we need to define. So go to right, click to here. Take the diagonal point and material you can say fluid. So how many times you need to define? 5 times because there are 5 channels. Okay. So likewise, and I need to copy this or because point is not copy. So what I can do? Go to points because I required points. There is no point. So I can generate points. It may happen that because of some problem, you may not. Okay. So I'm here, fluid. Remaining channel, I need to define fluid. This is also fluid. And this is also fluid. So likewise, I need to define fluid, define, yes, it is okay. Then now you can see that the inlet is here from the channel, but you can see the surface is total surface is there. So first what I will do, I will delete this surface and I can create simple surface 1, 2, 3, just a minute. This is also field topology. First I will save because here I need to mention where is the inlet. So what I will do, this total line create problem for me. So I will delete. Now this is the inlet for me. How I can do? Go and create the surface 1, 2, 3, 4. Again 1, 2, 3, 4. So this surface is get closed, that is inlet. Now I can copy this surface. Just a minute. I can copy this surface. This surface I can copy and translate it at in the direction of z 1 point, sorry, 4.2, sorry, 2.4, sorry, 2.4 into, just a minute, in the direction of z. And just forget 2.4 direction of z. So likewise, you can see here, you will get, then again 2.4 plus 1.2, that is 3.6, not 3.6 exactly, but you can copy with a 2.4, one by one you can copy this. Go to wireframe, select this and apply. Again, select this and apply. Again, select this and apply. So likewise, I am creating the inlet on all 6 parts. These are the inlet. How I can label? Create part, say inlet. And I can select the surface like this 1, 2, 3, 4, 5. I think I created 6. Okay, 6 channel, no problem. So inlet will be, now you can see, if I remove, I can see the inlet. Okay, this middle part is missing. Just a minute. You can add part inlet, sorry, inlet like this. The last one is missing. So again, wireframe. Yes. So this is the way how I can write the inlet wall name. Same thing I can do for another end, that is for outlet. So what I will do, again I will delete the surface, and I can transfer these walls, this wall, this wall, this wall. Sorry, we need to select very carefully because there are many surfaces. In the direction of x, how much? 15 mm. Z0. So you can see this is the way how we can transport. Now I need to give the label, create part, say outlet. Outlet. I will go to wireframe. Which are the outlet? 1, 2, 3, 4, 5, and 6 channel I have created. So inlet and outlet. Outlet with yellow color and inlet with a blue color. You can change the color also. If you go here, inlet, change color. I want red. Red or not. I want green. So green color will be the inlet and yellow color will be the outlet. Now I need to close the geometry, this geometry. So for that purpose, what I can do, I need to join this line, because initially what I did, I deleted that total line. So I need to join this line to create one surface. Continue. I think it will lose the connection. Save. We try to save the geometry first. Yes, save. Yes. So once we do this, then there is a surface creation. What I will do, I will close and again I will open. SEM. File. Because once you do the mesh, then remaining part is done by the computer itself. There is no as such intellectual is required. But as far as, so this we created the part inlet, outlet, surface, points. Okay. Now my aim to draw, close the outer part. One, two, three. Just a minute. Here there is a no line. One, two, three, four, five, six, seven, 8, 9, 10. Likewise, at micro level, you need to think. You should not select a wrong line, which may create the problem. Once again, we will do, or we'll draw a simple line and let me check whether it will work or not. Two, two, four. Oh, sorry. I draw the line at different location. Again, I will do 1, 2, 3, 4. Simply 1, 2, 3, 4. Okay, so I think it is creating problem, but we are having, if we do mesh to this, how it will be seen. I will show you. Then I will show you how to simulate it. Compute. Yes. So now you can see how the mesh are there. We are just looking at the water domain. Okay. For solid domain, we have not created the mesh because we unable to close the outer part. But in solid domain, you can see if you go to wireframe, so mesh will be look like this. And if you take this mesh for simulation purpose, then how one can do the simulation, that is a very important. So what we will do, so one can edit this mesh, check mesh, say apply, create subset, create, create, create. So we want to simulate flow through this channel only. And once we will get the mesh, we can save this mesh for the fluent purpose. Say accept. And on desktop, we are there. We have saved this. Yes. Here it is asking you how you can save. You can save with this, the fluent heatsink. So likewise, you can save the heatsink. Okay. So what it says, as it is 3D, here two sides are not closed. Okay. But for your purpose, I have one another heatsink that I will show you. A simple one channel. No. Just a minute. It will take few seconds. The process is simple. It means whichever the problem definition, the geometry creation and meshing will be the same. Once you do the meshing, then you need to go for a fluent. So fluent. Here I will show you the different case study of single channel. Okay. So I have one case study for, so you can read the mesh, go to read mesh. There is one project with me that I would like to show you. So here there is one channel instead of 6 channel. One can do a simulation of one channel also. This is the study of one channel. Same inlet at the one side, another, this is the inlet and another side is outlet. Same heat sink problem. So this problem I'm taking for the fluent case. Now you can see this is the generalized setup where you need to do for check mesh first. Whatever the mesh you created, you can go for check mesh. Then scale. What is mean by scaling? Whatever the geometry you created, that should be in a appropriate dimensions. Now it can show in meter, 1 meter, 2 meter, but my dimensions are in mm. So I can say mesh was created in mm, say scale. Now you can see the domain scale is going to change. So this is a very important task. Then pressure based steady state. I'm using steady state problem. Once I will do the generalized setup, I will go to model. In model, I'm using laminar flow. So laminar, say okay. Here the temperature is also there. I can go for energy equation. So this energy. Once I do this model part, then I need to go for a material. Here the default material will be air. Default material is air, but my fluid will be different. That is water. So go to Fluent database, select water liquid. Just a minute. Water liquid and say copy, close, close. And default solid is aluminum. If you want to take copper, go to Fluent database, say solid, and you can select the copper also. Copper, copy, close. So likewise, in your database, 2 solid material and 2 fluid material will be there. Go to boundary condition. Boundary condition at inlet, I can say 0.1 meter per second. Inlet 0.1 meter per second. And thermal, I can say 298 or 293 Kelvin is the temperature of inlet. Okay. So these two condition is very important when we are talking about the boundary condition. Then heat flux is there, which is at the base. Thermal, go to heat flux and give 1, 2, 3, 4, 5 and 4444, which is related to heat flux, that is 20 watt. Then Once you do this, this boundary condition is very important. Then go to reference value, say compute from inlet zone fluid. Sorry, here air means fluid zone, and go to solution initialization. So we are at last stage of fluent from inlet initialize, and last part is go for run calculation. Here you can give any count. I can say 10. I can say 10,000. Go for calculation. Now, what it will do? It will take continuity equation, which is a white line. X, Y, Z is a velocity, that is a momentum line, and Z, the last one, that is the energy. So likewise, it will calculate, and it will take its own time. It means one solution will get converged, at that time it will stop. So we will run for few iteration, and then we will go for post processing, how we can see the results. Okay, we will do some iteration, and then we will go for a post processing, because it may take time. So because of time constraint, we can avoid. So we will at least go for 20 iteration, then we will stop this problem, and we will write the solution, and then we will see the results. That we will do. 17, 18. So it will not require more than 10 to 15 minutes to converge the solution, because instead of 6 channel, we are taking a single channel for simulation. So what it does, it avoid the more computational time and memory. I can say stop. It will stop. Just a bit. Yeah, done. What I will do, I will write this, whatever the equation, whatever the solution I'm here, I will write. I can say iteration 23. I'm writing in the form in that way. And I can say here calculate. It will start the calculating in background. Then again, I will go for a next tool, that is a CFD post, where I can see the contours, vectors, and temperature plot. That is called as CFD post of ANSYS tool. File, load results. Where it is? It is in my computer, Kavan, and iteration 23. This one. You can always take .dat file, because it contained the solution. .dat file. Yes. This is a single channel. Now, what I will do, I will take one plot, location, plane. I will take plane. Which plane? YZ plane, because it is along the length. YZ plane. You can say apply. And I will take this plane inside the domain. Yes. This is good for me. Now I can see the contours. First pressure at plane and apply. This is the pressure profile. Inlet is at the higher zone. How much pressure? 2.78 Pascal. And it is a not a complete solution, because we stop at 23 iteration to visualize the results. Then temperature. So this is the temperature profile. Maximum temperature is 2337 e raised to 3. That is the maximum. As water is just entering from the channel, it is inlet. This is inlet. It means it required to travel this water from one end to another end, then we will get the complete picture of the solution. So this is the temperature. One can see the velocity profile also. This is velocity profile. And if anyone want to check the streamlines, go to streamline, and what I will do, I will off this contour. Where you want to see streamline? At the plane, apply. You can increase the point instead of 25, go to 100, and say apply. And if you are willing to see the animation of it, streamline, go here. So likewise, you can see, but the bubbles, whatever you are looking, that is too big, go to options, and you can scale down this bubble to 0.25, apply. Now look at solution is complete. Where solution is complete at 67 iteration. I can say okay, and I will write case and data file at, instead of 23, I can say I will give the number 67. Okay. So how much it take time? Only 5 minutes. Within 5 minutes, it can generate. And now you can see the temperature profile, which before what I will do of the streamline contour, I will say temperature, apply. Now it is at 23 iteration. I will load the results. Load results 67. Now you will see the difference. So the difference is not there. Just a minute. File, load results. Something glitch is there. Again, I will say load results. I will load the different results which I am having. Just a minute. Yes. So this is a solution already I have. So from that solution, you can see how the temperature profile is there. It means at the inlet, it is inlet fluid, and the temperature of the wall, you can see how it is there. So this is the temperature profile of the channel and fluid after the solution. So this is the way how we can see the results. We are at looking at the animations part, streamline. So that I want to show you, because that is important, because people are very much interested to look at the animation. So I can off this, and I can say uh, this one, animation. So likewise, you can see the animation, and you can store that animation to save movie. It will ask you where to save. I can say yes, desktop. On desktop, you can save. So here it is asking that you need to repeat how many times you want to repeat. So likewise, it will save the flow physics, how velocity is moving from one point to another point, and it will create the movie and it will save. I can say stop and close. So this is the way how we can see the contours. Vector is remaining. Just I will show the vectors, and we will conclude this session, because it is near about 2 hours we are going to spend in this total journey. So look at the contours here, vectors, where at the plane, say apply. So this is the vectors we can see. You can zoom in, zoom out. So likewise, the velocity vector, you can see how it is. So with this, I think my part is over about the tool, and we can go to our meeting. Yes, I can say the last slide about thank you that I want to show you, because uh, there is my YouTube channel, CFD for Engineers. So anybody can visit that CFD for Engineers, my YouTube channel. And with this, uh, thank you everyone. I can stop my presentation. And let me check the questions.
Thank you, sir, for such an insightful and informative session. Now
Yes,
we'll proceed to the question and answer session. I request all the participants to feel free to ask the queries. Sir, there is some question in chat box, I think.
yes, ma'am. Yes, ma'am. Please keep your mic and camera on. Well, thank you. Sir, how one can know which type of mesh is difficult in different geometry? So depending on the, if geometry is simple, you can go for hexa mesh. If geometry is complicated, then obviously you can go for a tetra mesh. And tetra mesh is easy to do. So that is the most important. Expand boundary condition in CFD. So mostly about temperature is concerned, there are two types of boundary condition. One is a constant heat flux boundary condition, and second one is a constant temperature. And there is a convective boundary condition is also there. It means if we know how much convection from the part, that is also is there. So that is about the boundary condition question asked by Anand. Then Aditya, how can we know the type of mesh used in different job? So it is a, how can we know which type of mesh? So simple way, go for tetra mesh, because tetra mesh is used for any kind of geometry. Complicated, simple, there is no problem. And uh, the result by using hexa mesh or tetra mesh is something different. It is not like that. You can use any mesh, result will be the same. In workbench is a different one. In workbench, everything is in a one screen. That is a meshing, geometry creation. Uh, but whatever we are using, ICM CFD is a separate tool by ANSYS, which is specifically used for meshing purpose. That is the answer from the question raised in a chat box. Any question? If anybody willing to ask, unmute their mic and ask the question. No problem. Yes, recording is already done by the college, and it is a live streaming. So recording is already on a live stream. No problem. One question is asked by Siva. That is, he's working on wall simulation. Wall simulation, I am facing the issue of velocity distribution. That velocity discontinue at the zone. I checked everything of current number interface, still getting some issue. So my number I am sharing in a chat box. So we can speak separately, because a specific problem need more time to explain. So we can talk. My problem, my contact number is mentioned in a chat box. So thank you, Nagaraju. So any question from participant, feel free to ask. Thank you. I think, ma'am, there is no question
Yeah.
because the session run for a total 2 hours.
Yeah, yeah.
So that may be
Okay.
the problem. But
Yes, sir.
but it is a required. Otherwise, only showing the PPT is not solve the purpose.
Yes, 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 sir.
And
So,
from my side, I want to convey that at Army Institute of Technology, we are running this CFD course separately for 2 month session. And for undergraduate student, we are giving the internship plus CFD training. So that we are doing for undergraduate student. And for MTech, PhD, there is a separate course that called as project-based CFD training for them only. Okay. With this, thank you, ma'am.
thank you. So, as we come to end of this session, it's my privilege to propose the vote of thanks. First and foremost, I express our sincere gratitude to our esteemed speaker, Dr. Sanjay Gaikwad, for delivering such an informative and engaging session. I would also like to thank our principal sir, for support and encouragement in organizing such academic activities. I also want to thank all the participants for their active participation. Once again, thank you all for being a part of this wonderful session. Have a great day, sir. Have a great day to all. Thank you so much.
Thank you, and have a great day to all. Thank you, ma'am.